up here. We're just putting together two rational expressions. We're doing it by getting a common denominator. And so on top we get ax plus a, and then you have x minus 3 times x plus 1. And on the other side, bx minus 3b, x plus 1, x minus 3. We're just practicing this because it's been a long time maybe since we added things up. And when you combine them all together, you're simply getting, right, when you have a like denominator, you can just add everything up and put it all together. I just want to make sure we're good with that step, that we know how to get a common denominator, add things up, and put it all together. Are you guys all okay with that kind of thing? Good, good, good. So what we're going to do today is we're going to incorporate this idea of adding rational expressions together, okay, into our final technique, which is partial fractions. So in our notes, our very first example is an example of where we're going to use the integration technique, partial fractions. Now, why do we have this new technique? Because if you look at this integral, it's different than anything we've done so far. We can't do a U substitution. It's not an arctangent. It's not a basic integration. And it's not a trig substitution because it doesn't have x squared plus a squared or x squared minus a squared. So we don't have any tools. But what we do want to do is make an observation, and I want to write it down, is that if we look at it, we see we have a polynomial on top, and we have a polynomial on the bottom, and we can't use any other integration technique so far. And so when you see polynomial divided by polynomial, that's when I want you to start thinking about this new technique called partial fraction integration, okay? So that's the key to think, okay, maybe I need to use partial fraction integration. And the first step in partial fraction integration, of course, is to take your original integral and make it simpler. And the way we make integrals simpler is often by factoring. So the very first thing I want us to do is factor that denominator in this rational expression. See it? Just put it there, John. I love that. Because that's actually what our goal is. Our goal is to actually rewrite this original expression, 5x minus 3 over x minus 3 times x plus 1, into its simpler form. And we just did that. It's going to be 3 over x minus 3 plus 2 over x plus 1. And how do we get that? We do that by solving and putting those numbers back in for a and b. But once we do that, let's see what we get. Why does that help us? Well, it helps us because now I have two integrals that are simpler and they're added up, which means I can separate those integrals. And I'm actually going to pull out my 3. And then I'm going to pull out my 2. And so why this is so good, this algebra technique of taking a complicated rational expression and making it into two simpler ones with factors, separate factors, because now I can integrate this. What's the antiderivative of 1 over x minus 3? What is that? It is. It's the natural log. So this is just the natural log of x minus 3. And what's the antiderivative of 1 over x plus 1? That's just the natural log of x plus 1. Beautiful. But do you see how simple that is when you get down here? Yeah, so let me get my key parts here. So what are my key parts to this method? Let me summarize that up for us. Let's get some key parts here. So my key part is recognizing, number one, that I have a polynomial over a polynomial. And so if I have a polynomial over a polynomial, I want to factor my denominator. That's my first thing. Recognize I have a polynomial over polynomial and factor the denominator. The second step is take each of those factors and use them to break up into a smaller integral with two dummy variables. So this is where we put dummy variables in. I'll just put dummy variables, A and B. Step 3 is where we actually solve for those dummy variables. Step 4 is when we replace back. And then step 5 is when we integrate. It's kind of really simple. So number 1, you recognize you have a polynomial over a polynomial and you factor. Number 2, you break it up into two separate, smaller rational expressions and put dummy variables in. 3, you solve for those dummy variables. 4, you put them back in. And 5, you integrate, okay? That's the method for partial fraction. Students find this one and they like this. They love it because the hardest part is the algebra usually.
Let's say like there's a cubic function on the bottom.
Yeah, we'll get to that one.
B, C,
Uh-huh.
going on.
If it's a cubic on the bottom, then we have to change what's on top. We're going to do one of those. Absolutely we are. Yep.
Back to the steps real quick.
Oh, yes, I will. Absolutely. There you go. Right there, James. Yep. Thank you for asking. Yep. That's a special case, John. Yep. So we'll talk about that special case then, hopefully by the end. You're good? Okay, good. So why don't you guys try this one? It's already factored for you, but what you want to do is make dummy variables on top of both factors. So I'm going to wander, and then you guys can ask some questions. This one's a little trickier, I think, John, or did you just see those numbers?
Yeah, I got A's 3, B's -1.
Let's see.
No, A3, A3 is yeah. Pretty sure. A3, B, yeah. You just like look at it and it just appears. Yeah, like
Can you?
I didn't work on anything.
Dang, you guys are really good if it just appears.
Took me a little bit of time, but
Oh, I messed that.
Isn't it 5A?
Yes, it is. Thank you. There is a 5A.
I feel like if you get more complex numbers.
You're just going to sit there staring at it for like 10 minutes.
Thank you. Yep. Okay, good. So like I said, you can do substitution, you can do addition, elimination, but the key is you want to get your system of equations and work it from there, okay? And let's see. So then I go back and I replace. So I have my integral of A3 over 2x minus 1 plus b negative 1 over x plus 5. And the key is we have two simpler fractions and they're being added so we can simply separate those integrals to make it into two simpler integrals. So what do we want to do with those two integrals?
We're going to have to log together.
They're both natural logs. So the second one is going to be the natural log of x plus 5. What about that first one? It is, but you have to be really careful. You have to put a 2 underneath. Because of that, if you did a u substitution, you would see it's a linear factor with that coefficient in front. And so we have to deal with that coefficient by flipping it over in front, right?
So let's say if there's a coefficient friendly.
So if there's a coefficient in front of your x, you have to make sure you deal with it by inverting and putting it on the bottom. How are you guys? How's everything? It feels good so far, right?
Yeah, until it gets complex.
It's pretty okay. We have a polynomial, we separate it into 2 smaller factors, then we do algebra to get those a's and b's, those numbers on top, those dummy variables, and then we just integrate. So of course we know it's going to get more complicated, right? So we're going to step it up a level. Does anybody have any questions on this example? Well then let's look at example C, okay? Yeah. Evaluate the indefinite integral. In this case, we have a nonlinear factor. And so, again, we're going to simplify this down by breaking it up into 2 smaller fractions. X on the bottom, and then x squared plus 16 and the next part, right? Do you guys see we have 2 separate fractions? Okay, now, did you look ahead, John? Tell me what we're going to put on top over here now. On top of x, what do we put?
Guessing you're going to pull a factor.
A, just a linear A, right? A dummy variable A.
It's like bx plus something.
It is. So on top of the next one, we're going to put bx plus c. But let's make an observation. Why did I put bx plus c on the second one? Because my denominator was what degree?
Squared.
2, right? Degree 2 squared. So what happens is the dummy variables on top have to be 1 degree less, okay? So if you just have an x on the bottom, then you just put a constant on top. If you have an x squared on the bottom, then you have to put a linear expression on top. What if, just question, what if I had like x cubed plus 4 on the bottom? What do you think I would put on top?
bx squared plus c
Yep,
plus d.
yep, bx squared plus cx plus d, exactly. So you always have 1 degree less on top. I'll just put that note down. So we'd always put 1 degree less on top with our dummy variables, okay? Does that make sense? Cool, yeah.
Did you start by pulling out a 3 or not?
Oh, God, yes. Let's pull a 3 out. Oh, I love it. Let's actually go 1 step down. I love it. Let's make our integral. I love that you guys saw that. Let's actually go 1 step down and pull out a 3. 3 goes into 96, right? How many times? 32. So let's actually pull a 3 out. I like that. I like that. So there's actually a 3 out front, right? Don't forget that 3 out front when we're moving on. Good. So that's equal to 3 times something over x plus something x plus c over x squared plus 16. So our job right now then is to find a, b, and c, right? Let's find those dummy variables. And we're going to do the same method as before. Well, John might have to do a little algebra this time because it's a little more complicated, right? Just a little bit. But we have a over x plus bx plus c over x squared plus 16. Let's get common denominator, get some system of equations, and see if we can't find a, b, and c. I'm going to walk around. That way you guys can ask questions as we go, okay? So you're going to get on top ax squared plus 16a plus bx plus c. No, bx squared plus cx. Is that what you got on top?
Yeah.
And actually, I wanna put my a's and b's together. So my a plus b goes with my x squared. My c goes with my x, and my 16a is my constant. I like to line them up like that, where I have my decreasing terms. And so then, yeah, A plus B,
That's just 1.
that's just 1. Absolutely it is, Max. Yep, so A plus B is 1. How about my C? What's my C?
1.
That's also 1 because it's the number in front of X. That's correct. So A plus B is 1, C is 1, and then my last piece is my constant, and my constant is just 32, right? So 16A has to equal 32. So it gives me a nice little clean system right here. I already know what C is, right? C is 1. I know that A has to be 2, and so that's so nice because now I can go in and find B, right? Yeah. Yeah. So let's put our dummy variables back in, right? A is 2. B is -1. And C is 1. And so I'm actually going to split this up while I'm talking about this.
Okay, I see now. I was doing 3 and
Good, I'm glad you see it, John.
You can pull that 2 out again and have 6 times it.
I can, thank you. I can have 6 times the integral of 1 over x dx. And what do I want to do? So you're right, that first one's going to get really easy, right? But first of all, did you guys all get the same A, B, and C?
Yeah. I think we might actually have to do
So what do we want to do on that next one with the x squared plus 16 on the bottom?
We have to do x plus 4, x plus 4. Do we have to do it again?
It's not factorable. Close idea. If I could factor it, I would go farther.
That's x minus 16.
Is it can I do u sub? If I let u be x squared plus 16, it gives me 2x. But then I got that plus 1.
Oh, yeah.
So wait, so what do I want to do? In fact, we had something like this on that 10 and 10.
Tangents.
It's kind of like an arctangent.
Look at the bottom, it's x squared plus a squared.
Yeah. That's the.
You guys got it. You have all the pieces together. What if I just give you a spur and help you out a little bit? Do you remember we had these? We did it in our 10 and 10. We did it on our prerequisite or our integration review. We did it in a group activity, and we did it in class. When you have this linear thing on top, negative x plus something, and x squared plus something on the bottom, we can split this up, right? We can split this guy up. And then the middle piece is just a u substitution, like you said, Max. The middle piece is going to be a u substitution right there. That's
Pull the negative out as well.
Oh, yeah, I would pull the negative out as well, too. Let me pull that negative out as well, too. Let me erase that inside, and let me pull that negative out as well. I like that idea. So I would do a u substitution, and then the next piece, it's kind of like an arctangent, isn't it? 1 over x squared plus 16 is almost 1 over x squared plus 1. But so it's an arctangent, but if you don't know exactly what it is, because there's a formula for this when this is not 1, I want us to make this into a trig substitution to practice. Trig substitution. Okay? And I think we'd let x equal 4 tan theta on that trig substitution. So again, I'm going to pause and stop and let you guys go forward. So you have 6 times the antiderivative of 1 over x dx. Then you have minus 3 x over x squared plus 16. You sub that. And then the last technique, 3 over times 1 over x squared plus 16. Try a trig substitution on that last integral. And I'm going to wander, and let's see what happens, okay? It's pretty fast. It's actually a very fast trig substitution. I like it.
Squared theta plus 1 is just secant squared, right?
What did you say?
Tangent squared theta plus 1 is just secant.
Yes, it is. Tangent squared theta plus 1 is secant squared. That's correct. Uh-huh. It's actually really nice, isn't it, the way it all works out?
What did that do? Nah, yeah, this is good.
How are you guys? Are you guys getting that arctan at the end? Right? Because theta, if you go back up to your relationship, theta, x equals 4 tan theta, so that means x over 4 is tangent theta, and that means then that the tangent inverse, or the arctan of x over 4, is just theta, and so that should give us the final answer. And see if you guys are matching. You guys, I think we should get 3/4 arctan, so I'll just write tan to the -1 of x over 4 plus c. My work's kind of all over the place, but let me see if you guys are matching, and I'm going to stop and pause and see if you guys have questions. Oh, you guys are so good. I love your formula doing. I love it, I love it, I love it. That was arc sine. That one was arc sine because a squared minus x squared first. Yes, with the square root. Very nice. Any questions? I want to do one more special case, if that's okay with you guys. Maybe two, but we'll do one for sure.
And the secant one would be
The absolute. That one I'd have to look at and make sure. But yeah, I think it's x times the square root of x squared minus a squared. But I might have to do that one out just to make sure there's not an extra a needed. Do you know what I mean somewhere? Yeah. But I would do that one out, but I think it's going to be that one. Yep. But we could do it with trig sub, right? We could we try it with a trig substitution and see what happens on it. Yes. Okay. So let's do these two special cases. That way you guys can do all your homework, and be all good and up to date on your homework. So here's your first special case, the next special case. This is when you have what's called a repeated factor. And it's a repeated factor. It's a repeated factor if you see a power up here on one of your factors. So if there's a power up there, then this is how we do our initial breakup. we would first put x plus 2 as a linear factor on the bottom, but then we would repeat it and put x plus 2 with a second power. Now, in each case, we have a linear factor that's being repeated, and so on top we would simply put a and b.
So one of them you just have the square root of the other one on the bottom.
Yes. So let me give you another example of a repeated factor. Suppose I have x squared plus 1, and I have it to the third power. So let's just say that's what's on the bottom, okay? Something on the top, that's what's on the bottom. And I want to break this up. So this time I have x squared plus 1, then I would have x squared plus 1 squared, and then I would have x squared plus 1 to the third power. When you have repeated factors, you have to take that power and you have to break it down. Do you see what I'm saying? Each time you would build it up.
Yeah.
Now, on top, because my bottom this time is not linear, it's quadratic, what would I put on top? I'd have to put ax plus b, cx plus d, and then ex plus f. Do you see that? Do you see how that would work if that's the case? So if I have a repeated factor, I break it up multiple times, but the things that go on top, my dummy variables, still have to follow that pattern of being 1 degree less than whatever that factor is on the bottom that's getting repeated. Ha! But okay, but now we'll go back to our example and see if we can't solve this one. So again, John, this is where it gets a little trickier too for you, right? So you want to put together a over x plus 2, b over x plus 2 squared, and this time, when you're adding these up, I think we only have to worry about multiplying that that first fraction, right? Because the next one, you don't have to worry about changing it at all, right? You can see that ahead. Very nice. Yep, so you'll have ax plus 2a plus b over x plus 2 squared. Oh, cool. So then you can see what a has to be.
A is 6, right?
A is the value in front of x. That's correct. Oops. And so that has to be 6. 6. And 2a plus b
7.
equals 7. Beautiful.
12 plus 8 is 7. B is -5.
Very nice. Very good work. So let me go back. So I have the first integral is going to be 6 over x plus 2.
Pull that 6 out of the way.
And the second integral is going to be negative 5 over x plus 2 squared. And yes, I would pull them both out just like you suggested, because it just makes it easier when you pull those coefficients out, those constants out, to deal with what's left over inside. And I'll let you guys think. I'm not going to solve anymore. I'm going to wander and let you guys think through that second one, what you want to do with that. They have lots of work studies, right? They should have lots of work. Anyways, u is x plus 2. You guys are doing x plus 2. du is dx. So you guys are doing on that second integral the antiderivative of 1 over u to the second, which you're rewriting as u to the negative 2, and then you're adding 1 and flipping it over.
So it's just -1.
5u to the negative 1.
Yeah, so 5x.
And so when we put that all together, it should give us 6 times the natural log of the absolute value of x plus 2 plus
Wouldn't it be like 1 over 5x plus 10?
hang on, I get plus 5 times u to the negative 1, which is x plus 2 to the negative 1.
I distributed the 5 in.
You can't distribute the 5 in. Why can we not put the 5 in? Because of that exponent, right? Because it's got that negative 1. But you can write it if you want, James, like that, right?
Yeah.
We can do that. So I'll just put a box around both of those because we could do either answer would work for me. Everybody agreeing? Sweet, sweet, sweet. I have one more thing to show then, and then we're done with partial fractions. I have one more to show you, one more method. But any questions? How are you guys on this? So if you have a repeated factor, you have to write it multiple times, okay? That's the key on this special case. Repeated factor, write it multiple times. Any questions? Then the last type of example that you'll encounter is this special case when your numerator has a higher power than your denominator. So like this example here is 4t squared minus 27t plus 28 over t minus 5. Do you see that the degree on top is larger than the degree on the bottom? In this case, the degree on top is 2, and the degree on the bottom is 1. Oh, and this should not be t. If I'm going to do t's, I'll put a dt there. Sorry, the degree on the bottom is 1. And so when the degree on top is bigger than the degree on the bottom, this is the last special case. So in this case, what we want to do is we want to use long division or synthetic if you can, but you want to use algebraic long division to simplify first. And then you might need to use partial fractions, or you might just be able to simplify past this. But your key here is you want to use algebraic long division to knock it down so you can get something workable. So we're going to review algebraic long division. How many of you guys remember how to take and divide a polynomial into a polynomial? Oh my God. Did we do this in Calc 2, Calc 1?
No, we did not.
We did not do this in Calc 1? Oh, yeah. So, right, you got this t minus 5, and you want to know what it has, how to get it to go into 4t squared minus 27t plus 28. You're right, and I like, Max, what you're thinking. You're looking here at this first thing. That's what I focus on first. And I say, what do I have to multiply by t to get me 4t squared? I need a t for sure, and what else do I need? 4, right? And so I'm going to put 4t up here. And now we multiply, right? So then we take that guy and we have to multiply it through. And we have to do it both to the t and to the minus 5. So what's that going to give us when we multiply through? 4t squared minus 20t. I love it. 4t squared minus 20t. And then what's our next step when we divide? We now subtract, right? Now we have to subtract. And so you might have learned change your signs. They might have said change your signs. And add down, right? So 4t squared minus 4t squared, and then negative 27t plus 20, negative 7t, and bring down that plus 28, right, to set me up for the next stage. And then we repeat the process, right? We focus in again, we zoom in again on that t, that lead term, but also negative 7t. We focus in on that. Yep, beautiful. So up top, we have to multiply by -7, so that when -7 multiplies through, it gives us -7t plus 35. And again, we're going to subtract. So I was always taught change your signs. So if it was negative, turn into positive. And add down, and that gives me a -7, I think. And so how do we write our answer? When we write our answer, let me just circle the parts. This thing on top becomes our quotient. This thing on the bottom is our remainder. And so when we rewrite it, let's rewrite our initial. The initial is always quotient plus remainder. Over what you started with, right? Let me put that down. So it's always quotient plus remainder over your divisor. In our case, I'll just write down t minus 5. So that would be my thought bubble. That would be my very first step. When my degree is bigger on top, I have to use the process of long division.
Reduce every single time.
Anytime your degree is bigger on top, you want to bring us down with long division. Now, what can I do now, John? What do we want to do now? Now we can separate, right? So I've got 4t minus 7 being my first integral. But then I have -7 over t minus 5 being... Do I have to do anything? I don't have to do anything further. I can just go straight through and integrate. So beautiful, isn't it? Ah, yeah.
Is there going to be nasty? I'm guessing there's going to be
Sometimes they'll get nastier, sometimes. But the cool thing is you have your process, right? Degree bigger on top, we use algebraic long division to simplify it down. And then if we have to go farther, we go farther. So antiderivative of 4t minus 7. So let me think. That's going to be 4 over 2t squared plus 7t. And that second integral is just going to be a minus 7. That's just a natural log, right? So I can put it all together as 2t squared plus 7t minus 7 times the natural log of t minus 5 plus c. Yes. Very nice. Any questions? Any questions? So at this point, we can do another example. I can just look for one, or if you want to look on your homework, I can show you. You'll have quite a few where you have to break it up. What do we want to practice right now? Do we want another long division one to practice? Do we want a repeated factor to practice? Do we want to break up things? I know you have to leave, Kayla. No worries. Try another long division one? Yeah, let's try another long division one. How about I do this guy right here? X cubed minus x plus 2 over x squared minus 4. Let's try that example, since that's next in my notes anyways. Let's see if we can't integrate that one, or at least break that one up. I think I want that integrated. Do I have that one? Do I have us doing one like that? Oh, there's another one. That one. No, yeah, so let's break that up with long division. Let's practice that long division one.
Tina,
Yeah.
Which one is what's it called with the integral of bx squared over the x times x squared? What's that integral? I mean, what's that called?
Which one?
I'm just trying to label with each example. So this one, what's this one called?
This one is when you have a nonlinear factor. A nonlinear factor. So you have a factor that is not linear.
Okay.
Yeah. But this is a good one where we'll practice long division first. Yes.
Yeah.
Let me see. So did you put an X on top? x cubed minus 4x.
Well, like, everyone's gonna play because it's scrimmage. But
Yeah.
when we get, I'm not gonna play until like the fourth.
Yeah.
Oh, there's only one step on this one.
Yeah.
There's only one step on this one. Why do I say there's only one step? Because we went right down to a linear factor here, which is 1 degree less. So this guy, you only have to do one long division. This is going to be quotient plus remainder over divisor. And we can integrate that first x. That one's easy. But this second one, what do we want to do with this guy? Break it up with factoring, right? We want to break that up at factor. So this guy here is the one that we want to use partial fractions on. The other one is easy. So this is the one we want to focus on and do partial fractions on. What is x squared minus 4? What can I factor that as? X plus 2 and x minus 2, yes. Oh, yes, very nice. So this first piece was long division. And that second piece is partial fractions. Oh, and I did not leave enough space. I can see that.
I have a question.
Yeah.
I might be thinking about this wrong, but we can't just split up into 3x over x squared minus 4.
We could, but then let's think about it.
Yeah.
If I did that, then 2 is over x squared minus 4. It's not in the square root, so it's not an arc sine or an arc secant. So it actually is just fractions. So yes, good thinking though. We could use a u sub on that first part. Actually we could, but then we'd have to figure out what to do with the second part, which is probably a trig substitution. So you could actually possibly get to it with a trig sub. Secant. Yep. So actually you could do it that way.
I think it's gonna be
Students tend to like this better because you get natural logs faster. Like, it's just that students tend to like this. But yes, I like how you're thinking there, Max. Absolutely. Lots of ways. You don't always have to do it one way. There might be multiple ways to approach it. Let me see. So I got ax plus minus 2a plus bx plus 2b. And then I get a plus b. Oh, this is a lot of work and I didn't leave enough space. I see that now. Plus negative 2a plus 2b. Oh, I can. And that's going to equate. Oh, that's going to give me a lot of good things, right? So a plus b becomes 3. And then I can factor out the negative 2 if I want, or if I want to leave it in. Yeah, it actually, it does. It gives you something really quick and easy to work with. I wonder if you guys are getting the same thing I'm getting. I get B is 2. And A is 1. So let me go back. I know I'm doing this so fast right now. I apologize. So that's the antiderivative of x, the antiderivative of x plus 2, and 2 over x minus 2. And let's see if you guys are matching. 1/2 x squared plus the natural log of x plus 2 plus 2 times the natural log of x minus 2. I think. Check, make sure I did my work right. This now. Hey Trey, how are you? I'm going to do homework if you want to come do homework in my office.
Yeah, I actually want to talk to you about something else.
Perfect.
Finish the homework.
Okay, perfect. I'll be right there. Yep.